Thank you, Chris. It's a real pleasure to be here at such a great event as this International Science School, and I hope the students, particularly those from interstate and international, are really enjoying the school. Today I'm going to speak about something that directly addresses the theme of the school, and that's light and matter. But I'm going to be talking about how the interaction of the two can be used to convert sunlight into electricity using solar panels such as the one that are shown up here. This is an area that I've been working at the University of New South Wales now for over 30 years. And it's a technology that, as you'll see during the talk, just starting to have some type of large-scale commercial impact. So a very exciting time to be involved with the technology. This is another view of a solar panel shown here. This is the silicon solar cell. It's made from an element silicon that is cut into this form of these very thin discs, such as shown here. You have an electrical contact on the front of the cell, and then right over the back, as shown here, you put some metal interconnects, solder them to the front, and interconnect the cells in series within this module. So all the cells are connected one to the other to produce the final module. The operation of the cell is really very simple. It's got to be one of the simplest ways of making electricity that's been perfected so far. All you do is put the panel out in sunlight, and electricity is generated between its terminals. So the operation is simplicity in itself. It's very much like a car battery. As long as the sun is shining on the panel, you can draw electricity from the terminals of the panel, much the same as you can from a car battery. So a battery like this might give you 12 volts of voltage, and if you put an appropriate electrical load across it, you might draw 20 amps from it. So it would give the product of that about 240 watts of electrical power output. This is about the same as a panel like this will give in bright sunshine. So the two are quite closely related on that account. One important difference, however, is a battery like this might have a life of 5 years or less. These panels will last essentially forever. So as long as the sun is shining, they'll be able to generate electricity. At present, the present manufacturers of them give a warranty of 25 years, although the actual life in practice is expected to be even longer than that. That's just a sort of conservative estimate of how long they might last. If you look at other products that have warranties, the only other product I've been able to find that has a 25-year warranty is a saucepan. So that's that gives you an idea of just how durable the panels themselves are. There's nothing that wears out in the operation of the cells. There's no moving parts, just electrons flowing around through the panel. This has been the most common application so far. Small systems such as shown here on the roof of private homes. A system like this, if it was 100% efficient, so if it converted all the solar energy falling onto it into electricity, would be large enough to power 2 homes. This system here, the conversion efficiency of the panel is not 100%. It turns out that there's a fundamental theoretical limit on the performance of the panel of about 30%. So that's a fundamental limit. The actual panels are about half that, so about 15% efficient. So rather than this being enough to provide 2 households, it'll provide electricity, about a third of the electricity requirements of an average home. So if you put 3 rows like this, this would provide the whole electricity requirements for the house. Of course, those of us that are working in the area are thinking of much larger applications in the long term. So this is an example of a couple of systems, very large systems that are being installed in different parts of the world. So this one's been installed on a old airstrip in the former Eastern Germany, an abandoned airstrip. It's providing power to the electricity supply network, just the same as a conventional power station is. Here's another large system here. So these are doing something different. In the case of the home, the panels were providing electricity predominantly for that home. Here is just pumping power into the electricity supply network for use by a unspecified customer. One thing I meant to mention was that when I was talking about the efficiency here, was that obviously if you can improve the efficiency of the panels, you're going to have some type of impact on the cost of the panels. So if this was enough to provide the whole home rather than needing 3 of these, obviously it's going to be less expensive to install and you're going to have less cost involved with mounting structures and frames and things like that. So efficiency is a really key parameter, and that's what our group at the University of New South Wales has been concentrating on, our research, trying to improve the efficiency and investigating other ways of reducing the cost. In particular, that 30% limit I mentioned is only a limit for this type of panel, the way these panels operate, that I'll be talking a little bit more about today. If you look at a wider range of possible conversion approaches, the efficiency limit can go up to about 70%, so that's what I think this type of technology will target in the long term. Okay, onwards, where might the technology go? This is a study by the German Advisory Council on Global Change, so a collection of people that had expertise in a wide range of areas, just looking at ways that we might sustainably provide the energy that the world's going to need over the next century. And this was their exemplary transition scenario, their preferred #1 scenario about how you might do that. So up here we've got plotted primary energy use in exajoules per annum, 10 to the 18th joules per annum. And at the moment, about 2010-11, we're using about 500 exajoules per annum. But that use is expected to grow quite significantly over the coming decade. So in this scenario, there's some sort of restriction of the natural growth rate that, that we could experience over the decade. So this 4 times increase in energy use is sort of a conservative estimate of what we might be seeing over the century. The different colours show how that energy is produced. So the dark colours at the bottom are gas, coal and oil, the fossil fuels, which is, as you'll see, is the main way that we produce our energy at the moment. So we're very dependent on them. However, the carbon dioxide emissions that are being produced by burning those fuels are already starting to create problems. And obviously, if you went through the century and multiplied the use of fossil fuels by 4, you'd just be in a completely untenable scenario. So I think we have to find an alternative to the fossil fuels to accommodate this increased use of energy that is anticipated. In this scenario, quite realistically, our dependence on fossil fuels is going to increase over the coming decades. Hopefully, it'll be mainly by increasing our dependence on gas, which is one of the cleaner fuels in terms of the carbon dioxide produced per unit of useful energy produced. But gradually, the increase in demand is taken up by alternatives that are more sustainable. So here we see in use of biomass increasing, wind starting to kick in a significant way. Wind's already used on large scale in Europe, but the total amount used is still not really significant at this type of scale. And then by about mid-century, starting to see solar come to the front as what was identified in this study as one of the few options that could sustainably supply the amounts of energy that the world's going to need by the end of the century. So by mid-century, 2050, about 25% of the primary energy in this study was imagined being produced by solar, and by the end of the century, about 64%. So this is a very optimistic scenario in that it's calling for a major revolution in the way that we produce and use energy, but it's the one that was identified in this study as the most favourable in terms of producing a sustainable outcome. So the industry presently not to be seen on this type of scale, but by mid-century it could be really quite a significant player. So those that are involved in the industry have this type of final application of the technology in mind. If we look at the amount of sunlight available, this is 0.02% of the total sunlight falling on the Earth. So there's plenty of sunlight available. You would only have to cover about 1% of the land surface area of the Earth to produce, a substantial amount of this type of level of power. So there's plenty of sunlight available. The sunlight is really quite a major resource compared to the amount of energy that's used in industry and so on. Okay, well, that's a brief introduction. If I just go through what I'm going to be talking about in my talk, it's amazing how this technology depends so much on some of the major advances of the 20th century. But I'll be talking about light. So the sun is the sort of dominant force in our part of the universe. We're talking about black bodies. So black bodies might conjure up different images in different people's minds, but in physics it's really quite simple what a black body is. It's just a piece of material that absorbs light with 100% efficiency. So by a reciprocal relationship, this means that it also, if you heat it up, it'll emit light as efficiently as possible. So it's some type of bound on the amount of light. It provides a bound on the amount of light a body at any temperature can emit. And the sun, although it doesn't look very black there, is in fact very close to being a perfect black body in terms of the type of light that it emits. And then I'll be talking about photons. So the solar cells are actually photon converters. They don't use the heat from the sunlight, they use the photons in the sunlight, so I'll talk a little bit about that. And then the solar cells are made from matter. So we'll talk a little bit about the material that the solar cells are made from, mainly silicon at the moment. There are ways of synthesizing materials that have similar properties to silicon. So silicon's not the only material that's possible to use in photovoltaics, but it's the predominant one now and it's likely to be for the next 10 or 20 years at least. And it's a very good choice in that silicon is one of the most abundant elements available on Earth. So, after oxygen, it's the most abundant element in the Earth's crust. So a really good material if you're talking about large-scale use of the technology. And then I'll talk about how light and matter interact to produce solar cells. And finally, I'll talk a little bit about the applications, about the challenges in trying to take a new technology that is still in its infancy and competing with established technologies. Okay, well, starting off with the sun. If you were to cut into the sun or dig into it, I don't recommend doing this. This is what you'd find. The outer photosphere of the sun, the outer surface, is quite hot at 6,000 degree Kelvin. But as you go towards the core, you probably can't see this scale here, but it's in millions of degree Kelvin. So you go right up in temperature as you approach the core to something like 20 million degree Kelvin. So the energy the source of the energy for the light that's being emitted by the sun is a nuclear fusion reaction at the core. So we're at the central bit of the sun, there's all this energy being generated. It gets transported through these layers of the core to this outer convective zone of the sun, where this is all by transferred as light through this region, although there's a lot of scattering of the light, and it's supposed to take at least 10,000 years for the light to come from this core to the convective zone. So it gives you an idea of the scales involved. But it gets to this convective zone, and then the heat transfer process changes. No longer is it transferred by light, but transferred by these convective flow of material in the little loops that are indicated. And then it gets to the surface of the sun, and the mechanism changes again to light emission, and the light gets emitted from this photosphere with a characteristic with characteristic features typical of that 6,000 degree Kelvin that I'll talk a little bit more about. Other interesting things, the sun is about halfway through its cycle, but as it burns up all the hydrogen in its core, it'll start burning the helium and progress through heavier and heavier elements until it gets to iron, when then things fall apart and the sun explodes as a supernova explosion. But the elements that we use here, the materials that we use in here, like the silicon, was originally generated at the core of a star like the sun and got scattered into space to then accumulate in the Earth's crust, as I mentioned before. So in some ways, all matter is essentially stardust generated in the nuclear fusion reaction at the core of these stars. So the silicon that we're using in a cell was once at the core of a sun and now is using the sun to produce energy. Sunlight's been around for a while, but Isaac Newton made quite substantial progress in trying to understand its properties. So the experiments that he did were quite simple, like just using prisms, which had been used before, to split the sun into different colours. So before Newton, it was thought that some way the prism was modifying the properties of the light to produce these colours. But the interesting experiments that Newton did was to show that the colours themselves were the primary things rather than the white light, which had previously been thought to be the case. So the ancients thought that the white light was the prime thing and the colours were some type of modification of that primary element. But this is the type of experiment, this is one of Newton's drawings, but split the light into the fundamental rays and then interestingly recombined them to produce white light again, using this lens here to refocus them back on the prism, produce the white light, then split it apart. So in that way he was able to show that the colours could generate the white light, so the white light was sort of manufactured by the colours rather than the colours being some type of modification of the white light properties. He also took individual colours and tried to split them further with prisms and showed that, you know, if you had a red colour, you know, you were stuck with a red, you couldn't create other colours from it. So those type of experiments there showed that the colour of the light was the fundamental property, and that was quite a big step forward. Newton thought of light as being corpuscular, made of particles. So, you know, given his contributions to gravity and so on, I guess this was quite a natural motion. So he thought these particles, you know, propagating towards a material interface like the surface of the prism would experience different mechanical forces as it approached the interface, you know, sort of an imbalance. If it's passing through a uniform material, either air or the prism, it's sort of a balance of forces around it. But as it got near the interface, there's a sort of imbalance created, which imparted a component of velocity towards the surface of the material and hence caused a deflection of the light away from its original path. To describe this effect, to describe the refraction of light in this way by an optical material, you have to you deduce that the light has to travel faster in the optically dense material rather than slower, as we now know it does. As was shown in the 19th century, it does. So, you know, the concept was wrong, but not necessarily the corpuscular notion, as we'll see. Newton also did some interesting experiments that he had difficulty explaining with this corpuscular theory, so he never really explained them properly. But these types of rings you get when you combine a flat surface with a gently curved surface are called Newton's rings. So he observed this effect and carefully measured, you know, the spacing of the rings and this kind of thing as a function of the radii of the material involved. So he quantified the effect quite well, but he didn't ever properly explain it in terms of his corpuscular theory. So that was left, you know, to the next century until this explanation came from Thomas Young, who then proposed the quite radical theory, and Newton's corpuscular theory was widely accepted, so this was quite a revolutionary concept that light was composed of waves, and he found it very easy to explain these rings if you assumed that light has this regular wave-like type of property. And the important parameter in Young's work was the wavelength of the light, the spacing between the successive peaks. But he actually took Newton's own data and showed that you could explain it quite well using this wave theory, and actually deduced the wavelengths of the different colours in sunlight that are quite close to the the modern accepted values. So if you imagine the light's a wave, it's quite easy to explain these interference effects, so that if a wave is displaced half a wavelength through travelling different distances or whatever, if you sum these two, you end up with zero. So the regions where you're getting no light in these patterns is a complete interference of the two rays. And then if the distance between the waves is a complete wavelength, they reinforce each other and you get the strong colours. So by looking at the spatial position of where the colours were, able to deduce the wavelengths of the different colours. This was at the beginning of the 19th century. The next topic I want to talk about is black bodies. So, we all know if you heat a bit of metal up, like in this blacksmith shop is being done, as you heat the metal hotter and hotter, it first glows red and then yellow and then white, as can be shown here. In the 19th century, there was interest in trying to understand the spectrum of colours that were emitted by hot bodies. And the black body was an ideal ideal emitter to look at, because it had the maximum possible emission of light of any colour because of its 100% absorption property. So you can see that this hot metal, down this region, it's pretty dark, and that's the type of thing that was often used, was metal coated with soot or carbon particles to darken it. It was quite common source. But also, if you have an oven and you have a little hole in it like this, if you had a cavity and little hole and you look into it, it looks quite dark, and the reverse happens if you're generating energy in that cavity. It looks pretty much as if it came from a black source. So this is where Max Planck comes into the picture. He was interested in trying to explain the nature of the light that was emitted by these black bodies. So this is at the end of the 19th century, beginning of the 20th century. So the measurement techniques had evolved to the stage where you could measure the nature of the light being emitted reasonably accurately. And this was the type of thing that was measured. This was the intensity versus the wavelength of light. So you're getting this peak in the intensity at a wavelength that depended upon the temperature of the body. And so this sort of course explains why the colour changes as you get hotter. You're moving the peak intensity further and further across the range of colours, eventually getting them all combined, around the 6,000 Kelvin. But the problem was the theories that of trying to explain the emission properties of these bodies couldn't explain what was being measured experimentally. So the experiments were accurate enough that had to be a problem with the theory. So this was the two theories. You could explain the properties at the long wavelength end of the spectrum. The Rayleigh-Jeans theory explained those. And then at the short wavelength end of the spectrum, the Wien theory described the properties there. But the two were clearly inconsistent. Like a little point here. Like in this region here, you can see that they both can't be right, and only one agrees with the theory. And similarly over here, they disagreement between the two theories. So Planck did something quite interesting. He first guessed the correct way of combining these two results. So he came up with a correct theoretical description for the curve, for the experimental curve. So the experiments were good enough that you could tell that this theory had to be correct. So that was the first step. And then he tried to see how he had to fiddle with his theory to get that theoretical prediction. So knew the result he was after from the theory, so what did he have to do to fiddle it? So he found he could get the correct formula if he assumed that changes within the black body didn't occur continuously with energy, but rather as little jumps in energy. So that's the tweak that he needed to be able to explain the expression he deduced. And this was the first introduction of a quantum idea into physics and resulted in the birth of quantum physics. Now, I'm not sure if that would have been, an idea that would have been taken up too quickly. Just this sort of mad scientist fiddling with formula and coming up with a result, making assumptions that, completely unfounded. But shortly afterwards, Albert Einstein got involved in trying to interpret another set of experimental data to do with the photoelectric effect. And this is now getting quite close to the photovoltaic effect on which solar cells are based. But these type of experiments using equipment like this was done whereby you shone light onto a metal anode shown here and then applied a voltage between it and a cathode shown here to see if you could get electrons emitted from the anode material. And you measure the number of electrons, they just create an electrical circuit, and you can measure the current due to the number of electrons being emitted from the metal. So this is the photoelectric effect. So the light falls onto the metal, this is the surface of the metal here, and you get electrons getting ejected from the transfer of energy from the light to the metal surface. The thing that couldn't be understood was that you got zero current measured from this meter unless you used light of a wavelength shorter than a certain critical value, a certain threshold value. And this threshold value, similar threshold's important in photovoltaic effect as well. So it didn't matter how intense, the natural thinking was before then, if you just turned the light up powerful enough, it was bombarding the surface with so much energy that you'd have to emit an electron. But that wasn't what was observed experimentally. You needed to have a certain critical wavelength threshold before you could get the emission. So Einstein realised this could be explained if the light arrived in tiny energy packets rather than continuously. So again, stimulated by the idea of Planck in trying to explain the black body radiation, just thought, well, one way you could explain this was if you had energy, if you had the light not coming continuously but distributed in tiny energy packets, in the same way that Planck had assumed energy jumps within the properties of the black body absorber. And the energy, this value here, a constant deduced by Planck from his work, Planck's constant times the velocity of light, which Einstein was very interested in, of course, divided by the wavelength of the light, was the quantity of energy associated with each of the packets. Now this is quite a tiny amount of energy. C is big and lambda is small, but H is very, very small, so it makes the overall energy tiny, but enough to excite a single electron from the metal. So that was the birth of quantum mechanics. So the fact that I'll just go back. Oops, going the wrong way. So the light had this dual property of coming in little packets of energy. So in some respects, it had to be a wave in some of its properties because Young had shown clearly that it was. But then in this type of interaction with matter, it had to be regarded as a little packet of energy, come in little packets of energy that depend upon the wavelength. So this, Einstein deduced that a photon was a particle that had properties beyond human experience. So sometimes it acted as a wave in some of its properties, other times as particles, didn't correspond to anything that we knew from everyday life. So people started thinking, well, photons got that type of property. What about the electrons themselves, which have been thought of as particles? Could we think of those as waves as well? So this identification of the wave part particle duality stimulated very quickly a lot of thinking about the whole range of material properties, not only electrons, but the properties of electrons in matter and so on. So a very rapid period of development followed Planck and Einstein's initial contributions. So now we have this picture of sunlight. So not only do we have the different colours coming from sunlight, but the sunlight's coming with little packets that have a combination of wave-like and corpuscular properties. So a combination of Young's and Newton's ideas on the nature of light. So the violet light, the wavelength is quite short, so the packets have more energy than down the red end of the spectrum, where the wavelength is about twice as long. So the energy of a violet photon, as these packets are now known, is about twice that of a red photon. Beyond the violet, there's the ultraviolet photons that have even more energy. These are the ones that give you sunburn, a lot of energy each packet, do a lot of damage. And down the infrared end of the spectrum, you have infrared photons. The peak intensity, if we look at the sunlight distribution, we can see the yellow curve there is the sunlight distribution outside the Earth's atmosphere, and shown there is a black body distribution at about 5,500 degree Kelvin. So you can see that the distribution of light reaching the Earth from the sun is quite similar to that from a perfect idealized black body in terms of the wavelength composition of the sunlight. Interestingly, the peak in the spectrum is in the range of wavelengths that our eyes are sensitive to. So this is either a result of evolution or grand design, depending upon your point of view. But this is the the fact. But plenty of energy at wavelengths beyond the violet, the ultraviolet here, and in the infrared down here. The sunlight gets beaten around quite a bit passing through the Earth's atmosphere. As you can see, the yellow curve is what arrives at the outside of the atmosphere, and then the red is what gets through. So there's all these absorption bands due to different gases in the atmosphere. So some are quite favourable, like the ozone absorption chops out a lot of the UV radiation that would otherwise be harmful. But water vapour and carbon dioxide in particular cause these other well-defined absorption bands in the spectrum. So only about 70 or 75% of the sunlight striking the outer atmosphere actually makes it down to the Earth's surface. And this is the radiation that solar cells here on Earth have to work on. While I'm talking about the absorption of atmospheric gases, where I'm standing, you're sitting on another very big black body, and that's the Earth. So the Earth's temperature is around 300 Kelvin, and it's emitting light of a wavelength distribution characteristic of a black body at 300 degree Kelvin. So in this chart here shows the wavelength distribution of a black body at 5,500, and then the wavelength distribution of a black body about 300 Kelvin. So wavelength range is shown here. So this temperature is about 20 times less than that, so the wavelengths involved are about 20 times longer. So we're talking about wavelengths, peaks around 10 to 20 micron range is where the Earth's emitting its black body radiation. What this grey chart here shows the absorption by atmospheric gases. So in the part of the spectrum where we receive the energy from the sun, we get these atmospheric gases interfering with the propagation of the light through the atmosphere, but it's not really too bad compared to the effect of the gases at the longer wavelengths where the Earth emits the radiation back into space. Water vapour in particular, this shows the absorption due to water vapour, very strong in absorbing light of this wavelength. So this is the black body emission, and this is what actually gets emitted through the atmosphere. So quite a beaten around distribution compared to the, to the ideal. But of course, carbon dioxide is not the most disastrous of absorption of gases in terms of its absorption properties, but the fact that we're pumping out so much makes it the most important greenhouse gas in terms of the impact on letting the light that is received from the sun escape from the earth. So if you have an imbalance in the two, you've got to heat the earth up to try in this direction here to increase the energy that's being emitted. Okay, and the photons here have quite long wavelengths, so their energy is very small, so they can't do too much with that energy. But one thing they can do is make a carbon dioxide molecule wiggle. So this is meant to be a carbon dioxide molecule with the carbon and the oxygen, and this shows the different ways that the atoms can wiggle against each other. This is the important one for the greenhouse effect, the heating of the earth by atmospheric trapping of the release of energy from the earth. So this sort of bending mode is the critical one for the greenhouse effect. So a little wiggling of these molecules might prove to be very important in the Earth's history. Okay, so that's an introduction to the properties of light that are important for the solar cell operation. So I guess the main thing that's important is that the sunlight can be regarded as photons. Oops. I'll just go back. There was one other point I wanted to make in relation to this spectrum here. One more. So the 19th century physicists were, and this graph is shown in terms of the energy emitted per unit wavelength, is what this graph is showing. We can work out how much energy each photon has using the equation that was deduced in terms of the wavelength of the photon. So we can convert a chart like this showing the energy distribution of light into one that shows the photon distribution of the light. So you just divide this, at each wavelength, divide this energy by the energy of a photon of that wavelength. And that's the important parameter when you're working in terms of a solar cell. It's not the energy that's coming from the sun, directly. That is, of course, just another way of looking at it. But it's the number of photons that is really the important property in terms of a solar cell operation. So you get a slightly different shape to the spectrum. It gets flatter down this end if you're dividing by a higher energy of the UV photons, looking at the number of photons coming from the sun. Okay, matter, and this is the silicon. The development of quantum mechanics allowed a more complete understanding of the nature of materials like silicon, and this is the picture that we now have of silicon. It has a core with 14 protons and neutrons, and then it has the electrons, 14 electrons, sort of circulating around outside the core. 10 of these electrons are in closed shells, so that they are not important in terms of the chemical properties of the silicon, but 4 of the electrons are in the outer valence shell, and they're very important. So silicon belongs in group 4 of the periodic table because it has these 4 valence electrons, and that determines its chemical properties. If it had 8, it would be a very stable material. The shell would be full, and like argon is the next rare earth gas with the with 8 electrons in the same core configuration, in the same shell configuration. So silicon has 4 shells in the outer shell, 4 electrons in its outer shell. Really would like 8, something worth remembering. So to make the silicon, put it in a form that's useful for solar cells, you have to produce it so that the crystal structure of the silicon is well defined. So if you just take silicon like this and melt it in a pot, it melts at 1400 degree Kelvin, so you have to heat it quite hot, or 1400 degrees centigrade actually. And then into this molten silicon, you dip a little preformed crystal, a seed crystal, and slowly cool the silicon that attaches to the seed. You can produce a very pure crystal of silicon, such as shown here. And this is what has been used in the past in solar cell work. So you take a cylindrical crystal like this, shave the edges off, still got a bit of the circular bit left here, and produce slice this up like bread, produce essentially quasi-square wafers such as shown here. So this is the traditional way of making silicon for solar cells. Much higher throughput, more rugged ways are now the commercial mainstream. So this is an area where the technology has evolved very quickly in the ways of producing the silicon in the form of these blocks and of slicing them into the wafers. Well, going back to this picture here, we have the little seed with the silicon attaching, and ideally the aim is to get a single crystal of silicon. So you get the silicon building up in a perfectly periodic arrangement within the solidified material. And silicon crystals grown like this are used in microelectronics, and for microelectronics use you need the crystals to be as close to perfect as you can get them. So this is probably some of the most perfect material that's used in any large-scale commercially silicon crystals that are prepared for microelectronics. Okay, this is another view. So this is looking along a very symmetrical direction along the diagonal, lining these two atoms up. So you can see the perfect periodicity of the lattice. This looks a little bit more jumbled, but it has the same perfect periodic structure. So you can see each silicon atom is attached to 4 others, and that ties up with sharing. Each silicon atom has 4 electrons in its outer shells. Each of the other atoms it's attached to contributes another electron, so that you get 2 shared electrons in these bonds that are attaching the silicon atoms together, performing this very stable structure with each silicon atom attached to 4 others. That was a 3D view. It's easier to draw 2-dimensional drawing. So this is the same thing shown in a 2-dimensional sort of rendition of the same effect. So we have the silicon atom here. It contributed 1 electron to these covalent bonds, and then this other silicon atom here contributed the other one, and that's performed this very stable structure. So these electrons are quite tightly held in these bonds, so that they're not available for transporting electrical current, for example, through the silicon. So silicon in this form here is an insulator, so you can't get the electrons to move out of these bonds very easily, so that you have a material that no free electrons that can move through them, so you can't pass electrical current through pure silicon like this. However, if you shine light on the silicon, something quite interesting happens, something similar to the photoelectric effect. The light has enough energy to break one of these covalent bonds. So a photon can break one of these covalent bonds, releasing the electron. So you start with a photon, the photon interacts with this bond, creates a free electron and a broken bond. The photon's annihilated in the process. So you end up, after the absorption event, you started with a nice bonded silicon, you ended up with a free electron and a broken bond. This free electron can now move through the silicon. It's not tied up in a bond, so nothing's stopping it moving through the silicon, so it can now transport current through the silicon. So if you shine light on the silicon, it becomes a conductor of electricity rather than an insulator. And also, interestingly, this broken bond can also contribute to electrical current flow. For example, electron in a neighbouring bond here can jump into that broken bond quite easily. There's not much energy required for electron to move from this bond to this one here. So if you think about it, what's happened is the broken bond has moved from here to here. And that's the way you do think about it in silicon physics. You don't think about the electrons jumping from bond to bond. You think of the broken bond moving through the material. and that's called a hole, a vacancy. And that can also contribute to electrical current flow. So you have the free electron that contributes, and you have the broken bond that contributes to electron flow. So two contributors to electron transport by shining light onto a semiconductor. And just like the photoelectric effect, there's a threshold energy for this. You need a certain wavelength of photon. You need a wavelength shorter than a certain critical value to get this occurring. So in the photoelectric effect, you're giving the electron, tied up in a bond, enough energy that it could escape from the whole material. Here, this is a more subdued process where you're just giving it enough energy to release it from the bond, but not enough to escape from the material. The other interesting thing you can do with semiconductors like silicon is that you can create conductivity in other ways. And this is the property that really makes silicon of such interest for microelectronics. You can add controlled quantities of impurities to silicon to control its electronic properties. So what's happened here is that we've replaced a silicon atom within that regular crystal structure by a phosphorus atom. And phosphorus is from group 5 of the periodic table, and it has 5 electrons in its outer shell. So if you imagine it, tied up in this lattice, 4 of the electrons in the outer shell get incorporated into these covalent bonds. So it looks just like silicon in that regard, but you've got 1 extra electron. Sort of think of it like Nigel no friends. Extra electrons that's in a different position from the 4 others. And it's very similar to a electron that's been released from a broken bond by light, for example. So this electron doesn't need much encouragement to move off and wander through the crystal, move away from this phosphorus atom. So if you add impurities such as phosphorus, group 5 impurities to silicon, you can also make it conductive that way. And it has a particular type of conduction. It's conduction associated with electrons, and fortuitously, it's known as negatively doped material, or N-type material is the common terminology. So I think most people have forgotten that the N refers to negative. It's become such a common terminology, N-type. So adding certain impurities, you can get this negative type property. And then you might have guessed it, but if you go the other way and add a group 3 impurity, it only has 3 electrons in the outer shell. They get gobbled up in 3 bonds, but there's not number 4 available for this 4th bond. So again, you've got the possibility of electron conduction by these electrons in neighbouring bonds jumping into the hole, and the hole's effectively moving off through the crystal. So you can dope the semiconductor positively, or p-type, by adding other impurities. And this is an effect that's very widely used in microelectronics. So finally, this is what a solar cell looks like. You have your wafer of silicon. This is representing a sort of cross-sectional view of those very thin wafers of silicon. But you arrange for a layer of the silicon material to have p-type properties and another layer to have n-type properties by adding group 3 and group 5 elements to the silicon in very small quantities. Just sort of parts per million quantity is enough to get the properties that you're after. So the silicon's otherwise pure, but just these very small quantities of dopants added. And this forms what's called a p-n junction, a p-n-type junction. And a p-n junction is the basic building block of microelectronics. So, your computers, iPhones, iPods, etc., wouldn't work if this p-n junction hadn't been discovered in the 1940s. So the photons come into the solar cell as before, and they release the electrons and holes from they release the electrons from the covalent bonds and thereby create an electron and a hole. Shown here as negative and positive charge. The sort of a negative charge sort of moving backwards is the same as a positive charge moving forward, if you get what I mean. The p-n junction is there actually to give a directionality to the flow of the electron in the hole. It turns out that the electrons can flow very easily through the n-type material, so they tend to head off towards the n-type material, and the holes can flow very easily through the p-type material. So it's the asymmetry in the properties of the transport properties in those two materials that give a directionality to the flow of electron in the hole. The electron then flows on through any electrical circuit connected across the cell terminals and then back and recombines with the hole to complete the circuit. That's the basic operation of a cell. The photons come in. Those above a certain threshold energy can create the electron-hole pair. So for silicon, it's actually in the infrared that the photon energy can be. So all these visible photons are great for creating electron-hole pairs. And then ideally for each photon that comes in, you get one electron and one hole. The electron goes through the circuit and recombines with a hole, but you only get sort of one charge carrier going through the circuit. So ideally for each photon that has enough energy, you get one electron flowing through the circuit. So it's a real quantum device. It's a one-for-one exchange between a photon in the sunlight striking the cell and an electron flowing through the lead. Because of various things like reflection from the cell and other things that that are not ideal about the cell design, shading by these contacts, for example, you don't get exactly one electron per photon, but you get quite close to it. Okay, and just in terms of the current voltage characteristics, the electron flow corresponds to the current output of the cell. If you, as you increase the resistance of the load across the cell and pumping current through it, that creates a voltage between the cell terminals. And this is how the current varies as you change the voltage across the cell. It stays pretty constant, then all of a sudden it can't go past a certain voltage output from the cell. You get this truncation of the current here. The power output is the product of the voltage and the current, so you just get this sort of linear increase in power output, and then around this knee in the curve here you get the peak power output from the cell, and that's the power output that determines the 15% conversion efficiency, the ratio of this electrical power at this peak to the power in the incident sunlight. Okay, I'll just finish up talking a little bit about applications. I mentioned before that there's these small-scale applications that are the mainstream now, and then these large-scale applications that are further down the track. The main difference between the practicality of these applications is the costs involved that you need to compete with the alternatives. So the photovoltaics works really well. It's really reliable, and as I said, sort of in principle can last forever. The only reason it's not more widely used at the moment is the cost. The technology is still quite young. This is what's called a learning curve, and it captures something that's quite common when you're developing new technologies, is that as you produce more of a product, the costs come down, like liquid LCD TVs, for example, costs skyrocketing down as more and more of them is produced. So this is quite, a widespread phenomenon. This is how the cost of electricity produced by photovoltaics has come down. This is a logarithmic scale as the amount of photovoltaics produced has increased. Again, a logarithmic scale. And you get approximately linear variation when you plot the data this way, for many products, not just solar. So, in the 70s, when I first started getting involved in this area, photovoltaics was really expensive and there was limited applications that you could use them for. But as the technology has improved and the product and the amount of product produced has increased and the manufacturing processes have become more refined, et cetera, the cost has come down quite dramatically, like well over 10 times. And if that trend can continue, if you just keep pumping up the volume produced, the cost will continue to come down, and there's no sign of that falling off at the moment. At some stage, you'd imagine you'd have to flatten out. No sign of that at the moment. So if you can keep pumping up the demand for the product, you're going to be able to reduce the cost as long as this learning behaviour prevails. So we're now at a very interesting stage. The cost of electricity produced using solar is coming within the range of conventional electricity supplies. As I said, this learning behaviour is quite common. You know, we've got cheap electricity from fossil fuels now, but that wasn't always the case. This is just a graph I found of the cost of electricity here in Sydney, you know, from the early 1900s when the electricity was first distributed, you know, to the present days. In the early days of electricity production, you know, electricity was expensive, only the rich could afford it. But as the technology matured and the generators for making electricity, etc., got bigger and bigger, the costs came down. It took about 50 years, then reached a sort of minimum, and then as environmental concerns increased and more environmental constraints have been put on the technology, costs are starting to increase again. When you think about it, there's no real reason that burning fossil fuels should be cheap. You know, like saw what happens with photovoltaics. You stick this panel out in sunlight, how much simpler could you get? If you look at what you need to generate electricity from fossil fuels, it's a really long, complex process. It's only really cheap because of this learning experience by the century of development that's gone into, you know, into the present equipment that you can purchase. But first of all, you've got to mine your raw material, like coal. You've got to transport it to the power station. Well, nowadays, you know, as a result of this learning experience, the power stations are built on the coal mines. The coal mines, you no longer dig tunnels into the ground, you just rip the surface layers off and get straight at the coal. So all that is an example of the learning experience that's gone into reducing the cost of fossil fuel electricity. Still got to happen in its entirety for other technologies such as photovoltaics. You then burn the material, you burn the coal, to heat water to create steam. And that's not a very efficient process, so you have a lot of waste heat that you have to dump somehow or other. You have a lot of byproducts from the burning. Some of them are now dealt with in a responsible way, like the sulfur dioxide that was creating problems, and the carbon particles that were getting emitted in the atmosphere. They're all captured now, but the carbon dioxide hasn't in the past been regarded as a problem, and there are procedures in place to capture that at the moment. That's still to come. The steam that you produce then turns a turbine, that turns a generator, that then produces the electricity. So many processes in sequence. So not a on the face of it, an inexpensive process, but made inexpensive by the century of development that's gone into refining every step of the process. Where we are with photovoltaics now, electricity somewhere in the 15 to 40 cents per unit range, depending on whether you've got big applications or small rooftop ones, etc. So starting to get quite a long way along the learning curve that the fossil fuel technologies went through. What we need to get the cost of photovoltaics down further is to keep increasing the market. And this just shows, you know, the photovoltaics is a very modular technology, so you can use just one panel, as in some of these applications here, or you can use, you know, large fields of panels, and technology works pretty much the same. So it just shows a range of different applications where costs are different. In the 70s, when I first got involved, this was the only application that was really commercially viable and there was a market for. And this was generating small amounts of power in remote areas, like in outback Australia. So this was one of the early systems. If you phoned Alice Springs, your telephone call would be transmitted over repeater stations like this that were powered by solar from the late 70s onwards. So sort of professional applications in remote areas where there's no traditional electricity supply. There's an enormous range of applications like this in developing countries, but although photovoltaics is the cheapest way of supplying electricity, it's economically viable. It's not affordable in that the challenge of having to pay for the capital cost of the generator up front is not well met by local financing arrangements and so on. But enormous market for photovoltaics in areas where there's no traditional electricity supply, particularly in water pumping where you don't have to worry about storing the electricity, which I won't have a chance to talk about today. In the Western world, the main applications are where you're connected to the grid supply, and even there's differences. The most challenging is this central station one, where you're just competing with conventional generators, such as in this system here. And here, all you're getting is the value of the electricity at the output of this station, which isn't very high. That's like the wholesale price of the electricity. If you look at other applications like the residential one, the economics are different because you look at it from the point of view of the homeowner. So the homeowner has to pay a different amount for the electricity than the person buying electricity from a conventional generator straight at its output. So that's the distributor of the electricity pays much less for the electricity than the homeowner has to pay. So hence the economics are different if you look at it from the point of view of the homeowner. It's like the retail price of electricity versus the wholesale price. So there's all these differences, within the market, and that's what makes the residential type of application the most interesting at the moment, in that the economics required are not as challenging as this application and are getting quite close to being met, as I mentioned. I won't talk about incentive schemes, but some countries have adopted different incentives for promoting the use of new technologies such as photovoltaics to try and encourage their commercialisation and the amount produced and everything to drive down the costs. So that's been quite a common motive in different countries around the world, particularly in Europe and particularly in Germany. So feed-in tariffs, one way of doing it, or giving rebates, cash support for installing systems is another. In a house, the generation of the solar is not necessarily well matched to the demand of household electricity. So homes generally use a lot of power in the morning and evening, mainly to do with cooking meals and people getting ready for work, or nighttime heating or something like this. But what's happening in these systems is that during the day they use all the power they can, but sell any excess back to the grid. And what's really important now for the ongoing development of photovoltaics is what's called net metering, so that if you sell power back to the grid company, you get the same value for it as if you had to buy the power from the grid company at the same point of time. So that's all that it needs now for photovoltaics to be competitive with conventional, to be economic for retail type applications, particularly in countries like Australia where we have plenty of sunshine. Okay, Europe has great plans for solar, 12% of electricity by 2020 is their targets. Other countries like Australia don't have quite as ambitious plans, even though we have more sunshine. I won't have time to talk about a couple of other issues I was going to talk about with how photovoltaic interacts with the demand for electricity within the grid. So that now brings me to the end of the talk. I just want to summarise and see that I made all the points I was intending to when I prepared the talk. But as I've tried to explain, solar cells depend upon a lot of the developments in physics that occurred within the 20th century, particularly the first half of the 20th century, the understanding of the nature of light, the development of quantum mechanics, the understanding of materials like silicon, how their properties depended upon how their properties could be explained by quantum mechanics and so on. The solar cells convert sunlight to electricity. Presently 15 to 20% is what you can buy commercially. Our group produces the most efficient laboratory cells, which are about 25%. But they still work on this principle of 1 photon per electron, and there's some modifications of that idea that can lead to higher efficiencies. So I think maybe in 20 years' time we won't be dealing with these type of efficiencies, but efficiencies more in this range. There's potential to at least double the energy conversion efficiency that reduces the number of panels you need for a home installation, for example. Learning by doing was the other point I wanted to make. To reduce costs of these technologies, you need to develop the market for the technologies, and when you're competing against established technologies that have had, a century of period to learn by doing, you're at a natural disadvantage. You need some compensating mechanism if you want to get to the same low costs. And several countries around the world have introduced various schemes to try and do that, try and accelerate the development of the technology so it gets down to competitive costs and becomes self-supporting in its own right. And then I wanted to just talk a little bit about the electricity market. Electricity market isn't uniform. Electricity is has different value for different people. So if you're a homeowner, electricity has a different value from if you're a large electricity distributor, for example. And that opens up the application for early application of photovoltaics in an economically competitive way, even when the technology is not fully developed to its ultimate potential. So in Australia, like many other parts of the world, we're approaching this interesting grid parity stage where photovoltaic systems can compete with the retail price of electricity, provided there's the legislative framework to allow ready installation of the systems. So thank you very much for your attention, and I certainly hope there's some questions.